Hi, Assalamualaikum. For this video, we'll continue with topic of the wave vibrations, chapter 3, damping oscillation. Before this, we have discussed about the simple harmonic motion of mesoscale system and pendulum. So, in the real situation, of course, there will exist the friction force. Okay, even though the mesh spring system will not oscillate continuously, at certain point it will stop. So, for this moment, when discuss about simple harmonic motion, we try to neglect the friction force to make it calculation easier, since that the friction force will be smaller. But what happen if we can have a friction force big enough to affect the whole calculation? So here we have a mesh spring system, okay, in the horizontal with K, the spring constant. So the movement is same, except we have additional here, the damper. So from the calculation, okay, we know that the Newton's law here, to MA and the minus KX. This is what we have done before. MA equal to minus KX, Hooke's law. For the damping, we have another parameter we call as B and V. V is the velocity and B is the friction constant. So from here, we can do the mathematics something like this, okay? Since that we know A is d square x over dt square, differential, okay? D square x square. Can bring everything to the left. So V is dx over dt. Sorry, plus kx equal to 0. And then we can divide everything over m over m. So what we have here is this equation, okay? B over m, because B over m is equal to, B over m is equal to gamma, and K over m is equal to omega naught square. K over m is a natural frequency. Okay, I put the symbol B omega naught. Natural frequency for the mesh spring system if we not calculate the friction force. Okay. So right now, this will be the equation of motion. And what we try to do, actually, we want to find the angular frequency or omega for the damping system. So this will be the physical view. Okay, we can see that we can put mesh spring and put into the viscous water here, and it will slow down the pendulums. So if we discuss basically when we discuss about the spring, okay, we have discussed from the last video. We have a oscillation, okay, oscillation, cosinus and sine graph. But for the for the friction constant that put in this equation, it will affect the graph itself. So let me see it later. So to solve this again, since we know we want to find the new frequency, okay, we already know the omega naught square is equal to km. That will be the standard. We need to assign x first, okay, value of x. Usually we are using x cos t. Can put the plus not plus alpha. But right now, for dealing with the damping, okay, they have some complexity to do the calculation if we are doing it using cos and sine. So I suggest that you use to complex function, okay, and we define that because we know that x is a real function for z. So we change everything to z. Here z, z, and z. And now we define z as part of the a exponential j p t plus. What is pt plus alpha? Alpha is still the phase, okay, and t is time. P is a some parameter that we can measure. Okay, we want to find because we cannot put omega here since we doesn't know the real point of the omega, and this will be something that we try to find from this equation. Okay, z will be equal to a exponential j pt plus alpha. Differentiate. For those who do not remember how to differentiate the exponential, to differentiate exponential will be easier because when we differentiate the exponential, it still maintain here. Exponential j pt plus alpha. A is a constant at the front, not affect the differentiation. And we differentiate inside. Since we differentiate inside here, we have jpt plus j alpha. Alpha doesn't have t here, so it will be 0. So we differentiate only jpt. Differentiate jpt, we can get j and p. J, p. And we know that a exponential jpt is z. To make simple view here, jp z. Next, we differentiate this equation. J, P, make some space here. A exponential J, P, T plus alpha. Since that when we try to differentiate the exponential the same, A is a constant, JP, so the still the constant. Differentiate inside, same again, we can get J and P. So we have here J square P square A exponential J PT plus alpha, and j square is equal to -1. So we have here -1 minus p square, and a exponential jpt is p z. Sorry, z. Okay. So now we have this equation. Is what we need to do is here. We need to put everything, substitute inside this equation. So what we have here, dz, d square z over dt square. So we can replace with the minus p square z. So we have here minus p square z plus gamma dz over dt is j, I need to put j in front, j p z plus omega naught where z equals 0. You know that z is still in the, we can cancel out again. Then we can use here minus p square plus j gamma p plus omega naught square z 0. Right now we have something interesting because this p have two places, okay? One in the real part and another one in the imaginary part. So we can define that p is a complex. So p is a complex. So for complex, we introduce a new equation for p, which is p equal to n plus js, same here. Y, same with the equation z equal to x plus j y or I. So this is a complex function, real part and imaginary part. So now we define p plus n js. What we should do, because from here we can replace the whole equation here. So we have p square here, so we can get n plus js square. Make this easier, we can square this immediately. N square plus j square s square plus 2njs, and then n square, j is minus 1, so minus s square plus 2njs. Now we can put in this equation. Okay, we can remove z. what we have here, minus p square. So mean that's minus n square plus s square minus 2njs minus 2njs and then we have here plus j gamma p. So j gamma n plus j gamma js. So we have j square gamma s plus omega naught square equal to 0. Okay, remove z here. So j square is equal to minus 1. So automatically put here. So now we have 1, 2, 3, 4, 5, 6, 6 Newton. We have this one is real, imaginary, real, and real. So imaginary when we have j here, for real will be this value. So for imaginary part is here, is small there. So I can put here j gamma n minus 2 and js 0. This will be the imaginary part. For real part will be minus n square plus s square minus gamma s plus omega naught square equal to 0. First, we solve this. Okay, j gamma n equal to 2 and js. Can cancel j dengan n, j and n here. We have gamma equal to 2s. So s is equal to gamma over 2. Since we know gamma, s we doesn't know. We can replace s here with here, n here. So we have here minus n square plus gamma over 2 square, means that gamma square over 4 minus we have gamma times gamma become gamma square over 2 plus omega naught square equal to 0. So we can bring n to the one side. So we have n square positive. We have your omega naught square. And for this, we can times 2. And also times 2. We have 2 gamma square. This over 4. 1 minus 2, you can get minus gamma square over 4. From here, we can define is n equal to omega naught square minus gamma over 4. This unit is a s minus 1 or hertz. So it means that this is a angular frequency. So n, we can define that n is a new omega. Okay? This n will become a new omega for the damping mass spring system. So from here, we know that omega naught square is k over m. Means that if the value here, which is the friction, very small, near to 0, means that the frequency for the system will be equal to omega naught square, k over m. Okay. Is it complete? Not yet. We need to find the equation of motion for mass spring system. Since we have here, we are using z. So we have here z equal to a exponential j pt plus alpha. And we know that p is equal to n plus js. So we have here a j n plus js plus alpha. And split this A exponential J N exponential J square S exponential J alpha. J square S means that minus, okay, we have here Z is equal to A exponential minus S exponential J N plus alpha. And we know several formula from here. So we can put here Z equal to A exponential minus S. S is a gamma over 2. Okay. Minus gamma over 2. And then we have here exponential J N. Okay. N is a omega. Omega plus alpha. Omega T plus alpha. T plus alpha. I think we forgot to put T here. Yes, they have T here. T. So they become J and T. And J is T. So we have here, sorry, minus ST. J and T plus 2. So we have here gamma over 2 times. Okay, they have time here. Because of Z, the real part of the Z, because we're dealing with the real part only. So we can have a X equal to A minus gamma over 2 times T cos T plus alpha. Because we know that exponential J theta is equal to cos theta plus J sin theta. Since J sin theta is not the real part, okay, imaginary part, so we only take the cos theta here. So this will be the new equation of X for damping oscillation. This is a very interesting one because A exponential minus gamma square T, this will become amplitude, and this one is a oscillation. We know that cos omega T is something like this. But the amplitude is everything's A. But right now we have a exponential minus. Okay, something T. And it will reduce the amplitude of this graph. So this will create something like this. Which is, this is cos omega T inside. The omega T means that the T period here is same. Okay, for one cycle. Even though it will reduce the amplitude. And the amplitude here, this will be the maximum when A, when exponential 0. So the value will be the maximum of A. And this will be the amplitude. We call it as a decay parameter. Decay parameter. It will decay until it will stop. So the oscillation will continue until it will stop. So right now we have this oscillation, and we have the equation here, d square x dt square plus gamma dx over dt plus omega naught square x equal to 0. Also, we know that a new omega here is equal to square root omega naught square minus gamma square over 4. So this three things will be really important to this equation of damping. Right now, we need to find what happened if the changing on the damping here, the friction. What happened to the system? We know that when the gamma very small, that maybe very near to 0, then we can get the omega is equal to omega naught. Or omega naught is a k over m. So right now, when they increase the parameter here, the system will still oscillate. Okay, we call it as a underdamping. Okay, underdamping when omega naught square here. So I think I need to bring this here. Okay, when underdamping, what we discussed before, this is underdamping. So what happened when the gamma is very small? So the system will oscillate. which is the mass spring system, will keep oscillating, but it will decay until certain time and will stop. How about critical damping and overdamping? So critical damping happen when this value is equal to omega naught square. So we have here omega is equal to 0. What will happen to the system? It should stop. No oscillation. There will be no oscillation. Okay. So this will be no oscillation. Same goes to the overdamping, because you can get the value omega is equal to square root minus. Something that you cannot solve. So what happened? Also, this doesn't have the oscillation. So the critical point will be the border from the underdamping to the overdamping. The critical damping will starting for the system will to stop oscillation. So I will show you from the graph. Right now, thank you for Nathan Alvin to produce very nice simulation here. So right now we have mass spring system that oscillate. You can say that this is simple harmonic motion. When we increase the damping here is 0, when we increase it, you can see that it will reduce. And very near it will stop. We try to increase the damping to 5 gram. We need to start again. It still oscillate, but after a certain stage, it will stop. And what happened to the system when we hit the critical damping? So I can click here critical damping and start the oscillation. They will put and it will stop immediately at the center. It will not oscillate. So what happened? I will increase the damping. Same goes. After that, they will stop, oscillate, and there will be no oscillation there. Okay, stop immediately at the center. So that happened to the damping oscillation. Same goes to the pendulum. You can see from the other videos done for them other later. It's very nice experiment doing to the pendulum. Okay, and friction will be magnet. You can see that at the critical damping, the pendulum, when we release, we will stop immediately at the center. So that's for today for this video. I hope you can get the clear view on this damping. The mathematical part, because we are doing they have the imaginary part, that's why the calculation is a little bit tricky, but still is something that easy to understand. So hopefully you can meet for another video for chapter 4. Okay, bye.